this section is not in your current textbook, so you can just label this section geometric probability. It was such a good section, we went back to an old book, just so we could teach it today. We're going to take what we've been doing in bell work and take what we've been doing in class and put them together. So geometric probability. Probability that involves a geometric measure such as lengths or area. It's going to be a lot of what we've been doing the past couple days of taking the big shape and subtracting the area of the smaller shape to get a number. Now we're going to put them together to figure out the probability of getting that shaded region. In order to do that, there's an easy formula for probability of area. If we want to know the probability of hitting region B, which is often is going to be the shaded region in the picture, if we want to find the probability of selecting that area, you're going to take the area of the smaller shaded region and divide it by the whole region and all. So you'll find the area of typically the smaller shape, subtract it from the larger shape, and that is going to give you the region B, and you'll divide it by the whole shape again. And we're going to have a couple problems about that. We'll deal with all the vocab first.
So it's not the
Probability of the area, what it is, that is how you're going to solve the probability if you're given the area. Has anyone heard of a sector before? Do you know what it is? Do you know what it is? Sector, a region of a circle bounded by a central angle and its intercepted arc. Does anyone know what a sector looks like? A sector looks like a slice of pizza. So we have our circle, we have the center, that is a sector. It's a portion of a circle. I'll give you guys the same challenge you gave the first two periods. Next time around to get pizza, instead of asking, hey, can you pass me a slice of pizza? Ask for a sector of pizza, and then come back and tell me the faces you received by your friends and family. They'll most look at you very confused. Now that you've seen a sector, if you ever played a board game with a spinner, the little areas, today we're going to find the probability out of what the chances are of landing on certain numbers or colors. So that's where we're headed. And if we know what a sector is, we have the formula to calculate the area. Now, what part of the area of a sector looks very familiar to you guys? Pi r squared. Does it surprise you that we use the area of a circle to find the area of a sector? We're just using a piece of the circle. That n is going to be the central angle, which is going to be the angle of each individual sector. Now, sometimes you're going to have odd-shaped sectors, and they're actually going to give you the angle. But if all the sectors are the same size, how can we calculate what the angle of each individual sector is? Let's say we have let's say our circle is divided up into 6 sectors. how can we calculate what the angle for each of those sectors is? Any ideas?
Divide 360 by 60.
Exactly. So what we're going to do is, there's going to be a lot of them where they're just going to give you all the sectors, but they're not going to give you the angle measurement. So you're going to take 360 and divide it by little n, or the number of sectors that you have. Whatever that number gives you will be the angle degree. And then once you have that, you're able to take it back into the area of the sector and then divide that number by 360. Sorry? The probability of a sector is really easy. You actually already calculate it when you do the area of a sector. N divided by 360. A lot of problems are going to have part 1, which deals with finding the area of the sector, and then part B or 2 of the question is going to ask for the probability. You really don't have to do any more work if you write out the formula for the first one. Just take the n over 360, and that'll be your probability of hitting that region. Alright, last vocab word. Segment. This shouldn't be any new information from what we've already learned about segments. Now we're just going to add it and apply it to a circle. I'll evaluate once I draw it. So the blue line would represent what the segments are going to look like in this section. It's the region of the circle bounded by an arc and a chord. And then this presents us with one of the fun problems of this section. We're going to now color in this little region up here and ask, what is the probability of landing in that small little area? Any guesses of how we can find that out using what we've learned in the past couple of days with the shapes? Besides this sector, what other shape do you see up there that is recognizable? Triangle. So we're going to do what we've been doing the past couple of days. Find the area of the sector, and then subtract the area of the triangle. And if they want the probability of hitting it in a whole circle, at that point you would just divide by the total area of the circle. Alright, now to take those words and actually put them into problems. The first one's really easy. We're going to start with testing, and I think you all can handle that. So on a couple of problems on the homework, they're going to give you a grid with boxes in them. And they're going to have a couple different boxes colored in. And they're going to say, what is the probability of landing on one of the shaded boxes? How could we find that out without actually finding the area of each square? Yes? Good. So how many shaded ones do we have for this one? 5. Now on the homework, the rest of the box is going to be pretty big. So I wouldn't take the time to count each individual square. But how can we find the total amount of squares in this? Multiply the sides. So I'll have 4 by 4, 16. So 5/16 is the probability of landing on one of those little shaded squares. So this is the basic steps of geometric probability. So now let's take it to what we've been doing the past couple of days. We'll bring back Miss Daniel's Tulip Garden. So what is the probability of landing in the shaded region? So you throw a ball into Miss Daniel's backyard, what's the probability of not hitting her tulips? The large rectangle is 9 by 15, and the smaller rectangle is 9 by 3. So the first couple of steps are going to be exactly what we've been doing the past couple of days in class. Where first we need to find what is the area of the shaded region. How can we find that region for this one? Bert, do you have any ideas for this one?
The area of the shaded region, we take the area of the rectangle, which is 9 and 3,
Okay.
27, and you subtract it from the overall area of the rectangle, which is 35.
Good. So we had the larger rectangle, which is found by 9 times 15, which was 135 units squared. And the area of the smaller rectangle is 3 times 9, which is 27 units squared. And so the total shaded region would be 135 minus 27. What does that give us? .108. So that, since that is the region we're looking for, we're going to put that on top of the top of our fraction that we'll be using. And we're going to divide by the total area, which is what? 135. So you've just taken what we've learned the past couple of days about finding the area of different polygons and different shapes, and that is now a probability. So what is this in decimal form? 0.8. So your answer would be 0.8, or what is that in percent? 80%. So if this is your percent chance of not hitting her flowers, you have a pretty good shot of throwing that ball and not hitting anything. Now how angry would she still get? I don't know. Okay, so this isn't too bad, right, so far? So far just dealing with rectangles. Let's change the shape. Trapezoid. Past couple of days I've just learned how much you guys love trapezoids in this class. So we're going to find the area of the shaded region. The top base is 14, the bottom base is 20, and the height is 12. What is the area formula for a trapezoid? Good. What do we get when we add our bases together for the trapezoid? 34. And what do we get for our height? Mike, can you tell us what you get when you multiply those together?
When you multiply 12 and 34, or
1234 and then divide by 2.
204.
204. So that gives us the area of our trapezoid. What was the dimensions we used to find the rectangle? Hey, what dimensions did you use for the rectangle? Mm-hmm. For the white rectangle, what did you use to find the area for that one? What two numbers? 14 times 12. Why would we not use 20 in this case? Very good. They're going to use that trick all the time. They're going to give you that measurement of the bottom, and that's going to be one of the big miss questions, is they're going to assume it's 20. And 14 times 12 is 160? 168. And so what number are we going to subtract from what to get the shaded region? Alright, and what number are we going to put on top of our fraction? 36, very good. And divide by? What do we get? 17%. Now with these, there's one step you actually want to do after you get your final answer. It's like a bonus question. Ask yourself, does my number make sense? So for this, there is a small shaded region compared to the larger region. So this is going to make sense. If you ever get a number that is over 100% or a negative number, go back and check your work because there's an error somewhere. There's never going to be a probability higher than 100%. Alright, now we'll go to Miss Daniel's favorite shape. Circle. So you have a rectangle which dimension is 3 by 4, and then 2 circles on the inside. Now, how are we going to calculate the area of those 2 circles if we aren't given a diameter or radius? Close. Good. So how would we be able to use that 4 to help us? Perfect. So here's 4. If we split that in half, we get 2. If we split that in half again, we get 1. Which is probably one of the nicest circles you'll ever find when you find an area. Because if we have 1 squared times pi, you're just going to equal pi. Which is probably also one of the coolest circles to find an area for, because then you have a circle that's with the area of pi. So that just might be a math nerd thing of enjoyment. Now, area of the rectangle, what are we going to do? So we have 3 times 4. What are we going to subtract from 12 to get the shaded region? Sorry? And what else? Pi again. So we're actually going to subtract 2 pi because of our 2 circles. What do we get? Good. 5.71. 5.71, is that going to be our numerator or denominator for our probability? Numerator? What are we going to divide by? 12. Now before even plugging this into your calculator, we see that it's 5 and it's really close to 6. And if we're dividing by 12, what should our answer be pretty close to? It should be pretty close to a half. So what is our final answer? 48%. This isn't too bad, right? This one we're just going to talk about. We'll actually go through because there's a trickier one next. For this one, this is pretty easy because the shaded region is its own shape. So what would we figure out how would we figure out the radius for that smaller circle? No. Yeah, so 8 would be the larger circle. What about the smaller circle? 4 would be the diameter, and you divide by 2. Now for 1, that's going to look a little tricky at first. Dartboard. So now you can figure out the probability of hitting the bullseye when you're playing darts. Now here's a tricky one like this, and this is actually one that comes almost directly from a book and how they often word it on test. You notice they don't put all of the measurements together on one side of the circle to make it real easy to figure out the diameters. They're going to put them on different sides of the circle to make you think a little bit. So the inner bullseye has a diameter of 1 unit. What about the gray circle? What is our radius for that? 3. Why is it 3, Gray?
Because you have the 2
Very good. When doing this, if you have the option to write on this, I would go ahead and just fill in this gap here. It tells us it's 2 over here, so it's going to be 2 over here, which is going to make it a lot easier for solving. When you get ones like this, if they're asking for the inner ring, it might be easier just to find all the areas of the circle, all the circles first, and then figure out the math of which ones you're subtracting. So for a larger circle, what is our radius? 5. So that'd be 25 pi. Our medium circle, as Greg told us, has a radius of 3. So we'll be at 9 pi. Then our area of our smaller one will just be pi. Now what circle do we need to subtract from another circle to get our ring? So you're looking at the very center one? Good. So this smaller one is the one that's cutting a hole in the middle circle. So 9 pi minus pi is what? 25.1. So that gives us the shaded region. And then what is going to be our denominator? 25 pi, because that's the largest shape. So that's one good thing about getting all the measurements first, because you're just always going to divide by the largest measurement. So 25 pi, you're going to be right around probably 78.5. So what is our decimal or percentage? 32. Now when we get to this step, one thing we need to be careful of is, one, you could always plug in and get that decimal first and then divide by the decimal. If not, just to be safe, always put parentheses around your denominator. Because when you punch it into your calculator, it's going to do order of operations. If you don't, if you just put 25.1 divided by 25 pi, it's going to take 25.1 divided by 25 and then multiply by pi. So parentheses are very important if you don't get the decimal first. Alright. Time to bring in sectors. So before we go with this one, we're going to look at one that's going to make a lot more sense first. It loads. So we have that spinner wheel. And we discussed earlier, if you want to know the probability of landing on one of those sectors when not given, we can take the number and divide 360 by that number. So if we have 4, what is the angle of each of those? 90. So if we want to know the probability of landing on each of those, what would we do? 90 divided by 360. So what do we get? 1/4. If we look over here at this chart, the theoretical percentage for hitting each of these is 1/4, which is what we just covered, which we calculated. So if we spun this wheel 4 times, what would we expect to happen? 1 each time? what happens in actual experimental data, there's no way to guarantee that's going to happen. That number we calculated at first was just theoretical. So it ended up, the pig never gets sprung on. So what could we do in our experiment to get our experimental number closer to our theoretical? More tries. So just for fun, we'll add a couple more shapes. So theoretically, each one should be landed on about 14% of the time. So let's just spin it 1,000 times. And you'll see they're pretty close. Earlier during prep period, I decided to see how many spins it would take to get pretty close. The closest we got took about 5 million spins to get them all close. And it just shows, if you, in science class, you talk about experience with stuff. In order to get good statistics and results, it can take a lot of data to figure it out. Luckily, there's no problems on your homework in which you're going to have to do it that many times. Homework is going to be more like this one. It's going to ask, what is the probability of spinning and landing on blue? So, in case, I know that it doesn't stand out real well, starting in this upper red sector, you have 40 degrees, 60 degrees, 50, 30, 40, 70, and 70. So those are our angle degrees for those. And they want to know the probability of landing on blue. Madison, do you know what number we'd put in the numerator for probability of landing on blue? So the key thing, especially on the homework site, is since obviously your worksheet is going to be in black and white, make sure to read all the sectors and make sure you have added up all of that color. So we saw there's a 50 and a 70. So that'll give us 120 in the numerator. And what are we going to divide by? 360. So what is our probability of landing on a blue? Good. That isn't too bad. That's a pretty good percent. So there's going to be a couple like that. All right. Now for the final question. I'm just going to give you a pre-warning. It is kind of awful. But we haven't lost any students yet doing this problem. We want to find we're not lost yet. We want to find the probability, I'm being nice to you, of landing in this shaded region. So, think about it this way. What's the probability if you take a bite of pizza that you're going to bite the crust? Now for some of you throw away the crust. Other people love the crust. So there's going to be two steps. There's going to be more. What's the two big things we're going to need to calculate in order to figure out that probability? Area of the circle. Well, for this one, we won't have to do the whole circle. For this one, yeah. So if we're doing a whole big, okay, let's do the whole pizza. What's the probability of getting that crust on that piece? So we're going to have to know the area of the whole circle. That's one thing. Can we calculate that right now? What do we need to know to find the area of the circle? Do we know the radius? What's the radius for this? 6, because they give you this whole thing, which tells us from this point to that point is going to be 12. So this side of the pizza is 6, and this side of the pizza is 6. And the area of the circle will be 36 pi. What other measurement are we going to need to know for this? Give it a guess, Greg. What else would we need to know?
Say how many pizzas we had.
That would actually be counted in the area of the circle. What's another shape up there we need to know? Triangle. This is going to be the trickiest calculation on the homework. So first, I'm going to redraw this triangle out here. There are two like this. Well, see, Miss Anna's a little jealous that you guys get tomorrow off, but we're going to be sitting in meetings. So I give you one challenge problem. You got a 4-day weekend. You can start it tomorrow night, sleep on it, finish it Saturday morning, because I know you guys are all going to be up early. All right. So we have 6 and 6. Now, what is the measure of that angle? Degrees. We have 6 slices of pizza, and if we divide by 6, each of these are 60 degrees. So this will also be 60. Another thing we're going to do is we need to calculate the height of the triangle. If I split this in half, what is this length up here on the other side? Sorry? What was the number you said? I think I heard it. Not 90. If these, okay. Good. 3. Each of these, since this is in a circle and we know this is a regular polygon, each side has to be the same. So this is going to be 6. But, so if we split it in half, they're each going to be 3. How can we calculate the last side of that triangle? Pythagorean theorem. So this is going to bring back the Pythagorean theorem in this section. So we have time so we can actually go through this whole problem. So we need to know this. So we know 3 squared plus b squared equals c squared. So what's 6 squared minus 3 squared? 36 minus 9. 25. Right? No. 27, thank you. So b squared will equal 27. And b equals plus or minus square root of 27. Which one of those are you going to use, plus or minus? Plus, because you have to have a positive number. So, this is the same thing as 3 square root of 3, which means we now have the height of our triangle. So the area of the triangle equals 1/2. Our base for one of these is 3, and our height is 3 square root of 3. What do we need to do in order to get this whole triangle piece, the area? Right now we just found one side of it, so what do we need to do? If we use 3 as our base, right now we're only going to get one of these pieces, so we're going to have to multiply by 2. So the area of the triangle will really be 9 square root of 3, because we take out that 1/2. And there's one more thing we need to calculate the area for. What is that? This sector. What was our central angle? 60. So you have 60 divided by 360. Pi times 36. So put that in your calculator and tell me what you get for that one. $18.84. Alright, now for the final piece. We have the area of the sector are going to subtract the triangle. So 18.84 minus 9 squared root of 3 is what? I'll give you a minute to plug that in. Once you get it, go ahead and shout it out. 3.25. And then what do we need to divide that by? Because that right now is the area of the crust. Divided by 36 pi, the whole circle. Because that 3.25 gives us that small little red sliver, and now we need to divide it by the whole pizza. So 36 pi. What is that final number? 0.09. Everyone else? 0.2. So the chance of getting that crust would be 2%. Those are the worst types of problems you're going to run into on the homework. There's only 2 of those. Now, you have a 4-day weekend. Most of this paper is going to be completed on completion. I want you to attempt the 2 that are like this on the back side. Also, hold on, give me back the ones I just gave you. You guys actually didn't get the worksheet. Now, one more thing. I'm going to spot check on correctness. Yeah, go ahead and get all of them. They're different. So, you have to be careful on your calculations because I'm not going to tell you which ones I'm going for a grade. Now, if you guys all attempt those 2 harder ones, then maybe I'll be nice and I'll grade those ones for correctness. But I need to see an attempt on those 2 harder ones. Now, other than that, was geometric probability that bad?
Yeah, it's hard. It's not hard, it's just not long. It takes a while.
Most of these problems are going to be on the shorter end, so they're not going to be as difficult as this. Today we